Hi, welcome to our presentation. This is Tonicello speaking. Our presentation will be on thermal action for structural analysis of existing buildings, case study and development. During our work, we did study two existing buildings with full sprinkler coverage. One has very large open space, and the second one is an industrial storage warehouse. We will present today this second case. The aim of the presentation and the case of the building is to comply with the Sàrl fire safety update and a compliance with 2020 standards. In this aim, we have to fulfill structural requirement R30 for 30 minutes of structural resistance with fire and analyze the possible expenses work for the structure and especially passive protection. Our solution is based on performance-based approach and design that will be done with advanced CFD analysis with and without sprinkler and a secondary advanced FEM structural analysis. The objective and the methodology of our work to meet the requirement of current fire safety standards, cost reduction and optimization, and find the appropriate and reasonable measure to meet this objective. For the fire safety engineering and performance-based design study, we will need several steps. The first one is an ISO fire analysis that allow to check the models and check the critical temperature for the structural elements. The second step consists in the analysis with the simplified methods and natural fire approach. This is done with compartment fire and localized fire. The third step, if the second one is not sufficient, will be done with advanced analysis with CFD and FEF models. In this case, we will study three stacks configuration as shown on the right. We will have one column with three different arrangement of the fire load. In red, you can see the starting fire. The building is made of two parts. On the left side, you have the arrival of the fresh product. You have pallets with plastic full of food. On the right-hand side, the pallets are empty, there is no food, but the height of the pallets are bigger. The structure is made of a composite slab itself made of continuous primary steel beam and secondary composite steel beam. We have unprotected columns. The building is fully sprinkled, and as said before, we have to achieve 30-minute fire resistance. The first step of the study will be done with ISO fire. In this step, we have checked all the columns and all the beams. The 30-minute ISO fire resistance is not achieved, as you can see, but we have found that the critical temperature are not too low, so there is a chance to advance analysis with natural fire where we can reach reasonable results. The second step is using simplified natural fire approach. We use localized fire as defined in Eurocode and XCC. You can see in the figure that the temperature that reach on the ceiling are quite high. And the temperature around the slab is at the maximum at 900 degrees. So we have very high temperature near the ceilings, and the columns, if are close contact with heating, heat very strongly. The primary result of this study is that the structural resistance of 30 minutes in the fire situation can be achieved with ISO fire, neither with simplified natural fire approach. This is due to the limitation of the simplified approach because no sprinkler is considered in the simplified model. In the advanced model, we can include the sprinkler with the aspiration model. And we did fix one condition, that's the first stack has a fixed heat release rate and is conservative. So we still have a fire, but we will not have propagation. That's we will show in the simulation. For this work, we did rely on scientific publication. There is a list of 3 publications that we did use, and especially the second one. For this, we have considered to add the sprinkler in the CFD model we are using for this study FTS. The results are available in the literature about the influence on the sprinkler and the fire resulting in thermal stress in the structure. The second study carried out several tests with 5, 10, 15 and 20 megawatt fire using different classes of sprinkler installation. For this test, the influence of the sprinkler on the gas temperature was measured. We can see on the figure that the higher is the flow of the water, the lower are the temperature in the ceiling. That's normal. In this case, we did adjust our model with the sprinkler installation that we have in the building. We did do several safety simulation to find results that were compatible with the tests found in the literature. We did add the pallet heat release rate, the sprinkler aspiration cone and velocity, and the fire propagation to other pallets. Now we see the result of this study. The first one is done with the polypropylene pallet stacks with fresh food. There is the model that we used, and you can see in red the starting fire stack. On this image, you can see that the fire is spreading through the whole pallets. The first finding on our simulation is that the maximum heat release rate is about 80 megawatt. And when you add the sprinkler, this power drops to 30 megawatts, and the fire duration is about 3 times shorter. This had influence on the thermal action and boundary that you can see on the figure, and we can find this result on the temperature itself. So you can see that without sprinkler we reach 800 degrees on the ceiling, and with sprinkler we only reach 600 degrees, but only for a short time. If we analyze the temperature on the ceiling without sprinkler, we have a great surface impacted, and with sprinkler we have a less severe action on the ceiling. We will show on this video difference with a scenario without sprinkler on the left and with sprinkler action on the right. It is clear that we have a fire propagation on the left-hand side, and we don't have propagation due to the sprinkler action on the right-hand side. So it is clear that the model is consistent with the assumption that the sprinkler doesn't
stop the fire, but limited the propagation as was in the assumption.
The second model was done with empty polypropylene pallet stacks, higher than the previous one. Again, there is the FTS model with the starting fire stack. We often use isosurface for temperature visualization. That is very effective to see where the temperature is and to show the clients good results that can be easily understood. Again, we reach the same heat release rate at previous because the fire load is the same but on a smaller surface, so the fire will be shorter. You see that we have 80 megawatt power without sprinkler and less than 30 megawatts with the sprinkler action. And this time the fire is a bit longer. Again, we see the thermal action on boundaries with temperature up to 1000 degrees without sprinkler. You can see that you can reach 1200 degrees without sprinkler and only 800 degrees with the sprinkler action. Once we have this temperature, this adiabatic temperature taken from FTS, we have to transfer this data to the structure with the temperature that we have extracted. To analyze the slab, we have to consider a bigger picture, so we did modelize one portion of the slab with all its components, the continuous beam, the composite beam, and the slab with the rebar. With this analysis, in all cases, we did reach a resistance that is longer than the 30 minutes required, so the temperature are taken for the full length of the fire duration and the slabs never collapse. The conclusion of our study is that the fire resistance of the complete bearing system for existing buildings needs to have a complete engineering approach to deal with different fire standards. A reduction, suppression, optimization of the passive fire protection cost is possible. The fire safety engineering methodology needs a first ISO fire approach with simplified models that is good for low heat release rate fire, simple geometry, and no sprinkler in the system. When this is more complex, you need to start with CFD analysis and FEF model for the structure. This allows to study complex geometry, add the sprinkler in the CFD model, and have an accurate structural analysis, including membrane effect, robustness of the structure, etc. With this project, we have very high cost savings as the fire authority validated the study and no protection was added to the structure. So the structure is left as it was before. Thank you for your attention. We are open to your questions.
Hey, Eric. So we're live now. Do you hear me okay?
Je pense que c'est bon.
Hello. We can hear you. Yeah, so for those who are watching now, Eric was teaching a class. He's in a classroom and he was showing the video to the class, and he's now chatting.
Okay.
Yeah. So
can you hear me?
Yeah.
Tac, on va voir si ça remarche là.
Yep.
Je pense que ça marche pas super bien.
Yeah, we can hear you. I am looking at what he's seeing though, and I don't think he can see me. So.
Okay, I hope you can hear me. I don't see the video. Okay, perfect.
So I'm just filling here.
Okay, the reliability of the sprinkler has been taken into account in the study, in general study. The effect of the sprinkler is an assumption that we take in the study to lower the gas temperature. Okay. The fire rate growth that is given by the Euro code, and we did apply it to the numerical model. It's about 1 to 5 minutes. For the fire ignition, we did apply it to the model on FTS. On the surface as the same as we we will do with material. So we did check the material and do it like we do always in FDS. So it's a normal model, nothing special.
Can you hear me yet?
We didn't use diabatic surface temperature. Yes, to take the result, we did take the adiabatic temperature. I'm sorry for the connection. It's not very good at the moment.
That's funny. Yeah.
If there is another question. We didn't take into account the temperature on an exposed side because it was not interested for the structural. Structural is just heated from the side behind. Okay, I can see you can see my class here.
Yeah.
You can say hello. Big conference.
Hello, class. It's a lot of people. That's great.
Voilà, c'était un peu chaud, désolé.
Oh, he lost it. So please answer your other questions here in chat. I think it was the best Q&A. Thanks again for participating. We'll go ahead and roll to the next slide now. So thank you very much, Eric. Thank you, class, for the disruption.